to know the position of the particle, if you know the force acting on the particle and at some initial time
know the position of the particle,
momentum, then you can get the trajectory.
If you know the force acting on the particle and at some initial
time
know the position of the particle,
then you can get the trajectory.
if you know the force acting on the particle and at some initial know the position of the particle,
once you know that, you can know the
get the trajectory. If you know the force acting on the particle and at some initial know the position of the particle,
but that is not possible.
the force acting on the particle and at some initial
So whether it is behaving like a wave or a particle or both or what, it depends on the situation, what you are doing. Okay? So how the particle is being disturbed, depending on that, it is decided whether it is going to behave like a particle or it is going to behave like a wave. So the explanation which I gave for the particle which is coming out from two slits, that is what is underlying this phenomenon. Now if we compare the particles, the properties of the particle with those of waves, basically a particle is characterized by its mass, position and velocity. And so when it actually collides with another particle, what is exchanged during the collision is the momentum and the energy. On the other hand, waves are characterized by their wavelength and frequency. And as a result of that, you see diffraction and interference patterns when you have waves coming from two different slits or something like that. So electron diffraction was one which was actually shown by Davidson in German, that you can actually diffract electrons and therefore there they behave like waves. So this was a direct proof of saying that particles do behave like waves at some time. And now it is being used as a characterization technique. You can also have diffraction of particles like neutrons, protons, helium atoms. So all these are being used for different characterization facilities as analytical techniques. Now comes this de Broglie wave hypothesis, that now we are saying that electrons do behave like waves. And in general, any particle does behave like a wave. So when it behaves like a wave, the characteristic of a wave is the wavelength. So can we associate a wavelength with a particle? That was the idea which de Broglie proposed. So he used the analogy with a photon, because photon, we say momentum of the photon is E by C. Now we are used to saying that energy is given in terms of quanta. So h nu, if you have the radiation frequency nu, then its energy is h nu in terms of quanta. And you can write this as C by nu, which is actually lambda. Okay? So using the same analogy, he said that if you have a particle with momentum p, it will have an associated wavelength which is given by this expression. So this was de Broglie's hypothesis, and based on this, as I told you, that if you try to calculate the wavelength of a particle which is of microscopic dimensions, like an electron, you will see that the wavelength is quite large. But if you try to find out the wavelength of a macroscopic particle, like a boy running, then the corresponding associated wavelength will be very small. So therefore you don't see the lumpiness, or basically you don't see the wave-like nature, because the wavelength associated is very small. So it is that the wavelength is associated with all the particles, but the macroscopic particles have a wavelength which is very small, and therefore it is not obvious that they will behave like waves, but only when you have very small, like subatomic particles, then the wavelength is large, and typically when the slit size is of the order of the wavelength, then you see interference patterns or diffraction. Otherwise, in other cases, you don't see them. In those cases, the particles behave like as particles, not as waves. So this is an important milestone in quantum mechanics, that you can associate a wavelength with a particle, moving particle, and which is related to the momentum of the particle. So basically, as I said, that the ideas of quantum mechanics fail when we go to the atomic regime, and therefore there we have to use quantum mechanics. And also in other cases which we may not come across just now is when the velocities are very large, comparable to the velocity of light. That time also relativistic effects become very important, and there also you can't use normal classical. So these are the regimes where quantum mechanics has to be used, classical mechanics fails. Now how do we define? So we have seen that for a particle which is behaving which is obeying classical mechanics, we can define the state of the particle by its position and momentum or velocity. Okay, and then what happens or how it evolves with time, that is given by Newton's equations of motion, and then you can find out the trajectory at all other times. Now what about a quantum particle? So a quantum particle is described by a wave function. Here I have written that it is a wave, but later on when we will actually go to the mathematics, we will see that it is actually called a state, or it is defined as a vector in the Hilbert space. Okay? So in quantum mechanics, what we say is you define the state of a particle or any quantum system by a wave function psi, which depends on its position. So if you are working in one dimensional case, it will be just dependent on x. If you are in 3 dimensions, it will be dependent on all 3 coordinates, x, y, z, or r, theta, phi, or maybe cylindrical coordinates. Depending on the geometry, you can use whichever coordinate system you want to use. So wave function basically but has no physical interpretation. It defines the state of the particle. You can get information about different properties of the material or the system from psi, and we will see later on how we can do that. But physically it does not have any direct meaning. Like as we say that position or momentum of a particle, you can actually visualize. That way psi has no visual sense. What is important is modulus square, and psi in general can be a complex quantity. Okay? So from psi, what we define is mod psi square, modulus square of psi, that is psi star psi. That is called, so psi is called the probability amplitude, you can say, and its modulus square is called the probability density. So mod psi square dx will define the probability of finding a particle or a system in serial space from between x and x plus dx. So this is the probability density or the probability of finding in a certain range. And psi can be determined by solving the Schrodinger equation. So we will all this we will do later. But basically the thing is, if you can determine psi, or if you know psi for a particular system, then you can basically say that you know all the information about the system, and you can calculate various physical quantities from psi. And psi you can determine by analytically solving the Schrodinger equation or computationally numerically solving the Schrodinger equation. So wave function is the state of the quantum system, a state vector in Hilbert space or an inner product space. As I said, so tomorrow, maybe tomorrow, day after tomorrow, when we get time, we will talk more about Hilbert space and vectors in the Hilbert space. But just now I just mentioned that it is actually a vector in the Hilbert space, not the vector in 3 dimensions as we normally talk about. So the modulus square of the wave function at any point in space gives the probability of finding the particle at that point. So in 1D, for example, here what I have shown is the probability, that is mod psi square, and here you see that between x and x plus dx, whatever is the probability, that whatever value you have of mod psi square at that point x, mod psi square into dx will give you the probability of finding the particle between x and x plus dx. And as I said, psi can be in general complex, therefore, but probability has to be a real quantity. Therefore, we don't just take psi square, we take mod psi square, that is psi star psi. So that is whatever the result you get is a real quantity, so it represents the probability, which is a real number. Psi is complex. Yeah. So in 3 dimensions you are talking about a volume element, say volume element d tau, which can be if you are in Cartesian coordinate system, it will be dx dy dz. If you are in spherical polar coordinate system, it will be r square dr sin theta d theta d phi. So PR, which is proportional to mod psi square, will be the probability density, and mod psi square d tau will be the probability of finding the particle at point r within a volume d tau. Now total probability of finding the particle somewhere in space has to be 1, because you have to find out the particle somewhere. So we say that probability can be integrated, and mod psi square dx in 1 dimension has to be 1, or in 3 dimensions when you integrate over d tau you will get 1. So this you say that so basically what we say when this is equal to 1, we say that this psi is normalizable. If you get some other quantity, instead of 1 you get some value n, then you divide mod psi by 1 upon root n and it becomes normalizable. So total probability of finding the particle somewhere in space has to be 1. So wave function has to be a normalizable wave function. Only thing that you get is if you are talking about a plane wave, that is not a normalizable function. So we have to use a different kind of normalization for such particles. Otherwise, if you are talking about a bound system which does not go to infinity, then you say that this psi is a square integrable function, and that comes because it is a vector in the inner product space. So it is always a square integrable function, and you can get a normalized value for the probability. Now, what are the other properties that a wave function has to satisfy? So, as I have not gone into I think Professor Kane will talk about Schrodinger equation. I am not discussing more on Schrodinger equation, but basically, psi is a solution of a second order differential equation, and therefore it has to satisfy certain properties so that the interpretation which Born had given, that mod psi square gives you the probability density. So, for that it has to satisfy certain conditions. So the first condition is psi has to be a continuous function. Then since there is second order derivative involved in the Schrodinger equation, first derivative also has to be continuous. So these are two mathematical things, that psi and first derivative of psi should be continuous functions. Psi must be finite everywhere. If it becomes infinite somewhere, then it will not be a normalizable function. So it has to be finite everywhere. And it cannot be zero everywhere, because if it is zero everywhere, that means the probability of the finding the particle anywhere is zero. So then it does not represent a real system. So these are 4 properties that the wave function has to satisfy, and pictorially I have shown here. For example, the first one, you see there is a discontinuity in the wave function. In the second one, you see a discontinuity in the derivative. In the third case, you see that at a particular x, you have 3 different values. So what does that mean? If you have a multi-valued function, the probability of finding the particle at one place is different. That is not correct. And last one is, it cannot become infinite. So these 4 functions that are shown here, they are not valid or allowed wave functions. So these 4 functions that are not everywhere. It can be zero. Somewhere it can be. At some point it can be zero. Where the probability of finding the particle has to be zero, it has to be zero. For example, when you will d particle in a box, infinite box, in the infinite where the potential is infinity, the particle cannot be found in that region. So there it has to go to zero. So these are the 4 properties that in general the wave function has to satisfy. In addition to these properties, depending on what system you are representing, so as I said, particle in a box, so at the sides of the box the wave function has to become zero because the potential outside is infinity. So like that, depending on what physical situation you are representing, there will be some more boundary conditions. You are solving a second order differential equation, so there will be 2 constants of integration. To get psi you will have to integrate it twice. So there will be 2 constants of integration. So those will be decided by from the boundary conditions. And these boundary conditions then lead to quantization of energy. So in general, these 4 properties the wave function has to satisfy. In addition, depending on the physical system, it has to satisfy certain boundary conditions, and those boundary conditions actually lead to quantization of energy. Yes. See, here it is only for one-dimensional case, so it is d psi by dx. If you are talking in say in 3 dimensions, then it will be a partial dimensional case. So it is d psi by dx. If you are talking in say in 3 dimensions, okay. So now we will come to the uncertainty principle. So in one of the experiments that I talked about, for example, the Feynman thought experiment, what we were trying to do is to find out where the position of the electron, or from which slit the electron is going. That means we were trying to find out the position of the electron. Okay? So the moment you disturb the electron, you see that it does not behave like a wave. If you don't disturb it, it was behaving like a wave. Okay, so basically what it says is you cannot determine the position or momentum. So basically we have not yet gone into the mathematics, but for each observable that you talk about in quantum mechanics, any physical quantity, for example the momentum or energy of a particle, for each observable you have a corresponding operator. that operator has to be an Hermitian operator because according to its eigenvalue has to be real quantity. It has to be an Hermitian operator. And if the operators do not commute, all this I am just saying, we will actually do the mathematics later, I am not doing the mathematics here. But if the operators do not commute, then that means that the corresponding observable quantities cannot be determined absolutely precisely simultaneously. So when we say that this uncertainty principle is delta x, delta p has to be greater than some h cross or h cross by 2 of that order. It has to be of the order of h cross. So what does it mean that,
So what does it mean that talk about measuring certain value? For example, if we want to measure a current by an ammeter, so we say that it should not draw any current itself.
Yeah.
Okay. So if it draws the current, then it disturbs the value. So can a similar
That is a limitation of the instrument. This is not a limitation of the instrument. This is basic thing that you cannot. It is the indeterminacy come from the nature of the system. Quantum system has this. So this indeterminacy has nothing to do with the instrument by which you are measuring. There it happens because ideally it should not draw any current, but it is drawing a current. Therefore but that's what I said. It is a limitation of the instrument. Here it is not a limitation of the instrument. You might have an instrument which can measure momentum very accurately, but if the particle is not exactly at one position. So basically what does it mean is, if you can determine the momentum accurately, then you cannot say anything about the position of the particle. So the particle can be anywhere from minus infinity to plus infinity. Or if you can measure the position accurately, then there will be an infinite uncertainty in the momentum. So this is basic property of a quantum particle. As I said, that the corresponding operators, mathematically I can say that corresponding operators do not commute. So basically the wave function is not an eigenfunction of any of these operators. So you cannot determine it. And we will talk about superposition and things like that, then we will come to know what actually happens when you do a measurement and then to which state the particle goes. So basically it says that the position and momentum of a quantum particle cannot be determined accurately at any time. So there has to be some finite value of delta x and delta p. That is what is meant by uncertainty principle. So this is an experiment again with electrons, diffraction you are doing. If you have larger openings, here for example, the slit is very large. So there is a large uncertainty in the position. When I say that the electron is going through this slit, actually I don't know whether it is going from here or here or here. So there is a large uncertainty in the position. Correspondingly, there will be less uncertainty in the momentum. Okay? So the spread that you will see will be less. On the other hand, if you say that the slit is very small, then you have very small uncertainty in the position of the electron. That time the momentum uncertainty will be large. And correspondingly you will see that in the diffraction line. So this is another example where you see the uncertainty principle into picture, coming into picture. So this is basically, it was given by Heisenberg. It is impossible to specify simultaneously with precision both the momentum and the position of a particle. And if it is described, it is not actually a quantum system that you are talking about. It may be a. So basically, you cannot, for a quantum system, you cannot describe this accurately both simultaneously at the same time. And there can be. So as I said, that for macroscopic particles, delta x and delta px are very small because corresponding. So basically, when h is very small, h tending to 0, you go from the limit from the quantum system to classical. So h cross tending to 0 is actually a correspondence from a classical system to a quantum system. So in macroscopic cases, therefore you can measure the position and momentum quite accurately, because actually the thing that you are measuring itself is quite large as compared to the error that you have in that measure.
itself is quite large.
So understanding the uncertainty principle, basically what I am saying is, suppose I am saying that there is a particle localized at this particular position.
Basically what I am saying is, suppose
Then it would mean that there is a large uncertainty in its momentum. And therefore delta px is large. So many waves of different momentum in the space, that there you know the relation h cross k is equal to p. K is the wave vector corresponding. So there will be large variation in the corresponding wave vector. So basically you can represent this as a superposition of many waves. And this actually superposition of many such waves gives you the describes a localized particle. So this superposition of such waves is what we call as a wave packet in quantum mechanics.
So this superposition of such waves is what we call.
So a wave packet is a localized mathematical wave function used to represent a quantum particle. By superimposing multiple plane waves of slightly different wavelengths. So again you use the relation between lambda and k, wave vector. The waves constructively interfere in a small spatial region where the particle is actually localized. So there only you will have the magnitude of the superposed wave as large, and at other places you will have a very small magnitude. So you can represent a localized particle by a superposition of plane waves.
So you can represent a localized particle by a superposition of plane waves.
So mathematically we write it as a Fourier transform. So if I know psi at some time t equal to 0, I can write it as phi k e to the power kx, where e to the power kx are the sinusoidal waves. The phi k represents the amplitude associated with each wave. So this is basically the Fourier transform. So phi k can be written in terms of psi of x0. So this is the relation between the Fourier transform. And then you can, from that you can calculate the time evolution of the wave function. So at some other time you will have e to the power I kx minus omega t, and omega is replaced here by h cross k square upon 2. So this represents, for example, a wave packet where the value of the final value of the state is large. The particle is localized in this region, or maybe slightly less probability in this region. At other regions the probability of finding the particle is less than that. K is the wave vector. H cross k is the momentum of the particle. So k is the wave vector.
H cross k is the momentum.
So what are the properties of the wave wave packet? Localization and probability. The amplitude of a wave packet envelope determines the probability density of finding the particle. The particle is most likely to be found where the wave amplitude is largest. Now with each wave packet you have a phase velocity and a group velocity associated with that. Phase velocity is actually the velocity with which the individual components in the wave packet they oscillate, and the group velocity is the velocity that the quantum particle will move with. Then there will be a dispersion. As the free particle moves, its wave packet naturally spreads out over time. And this physical spreading illustrates the increasing uncertainty in the position of the particle. And normally we know that the minimum uncertainty wave packet is the Gaussian. So all this is I am just putting here. I am not doing the mathematics. If the time permits, later on tomorrow we will talk about this. Yes. So basically, if you try to calculate the uncertainty, you will get the uncertainty will be minimum when the Gaussian wave.
Basically, if you try to calculate the uncertainty, you will get the uncertainty will be minimum when the.
Okay. Then 0 point energy is one other thing that is associated with a quantum particle. That if you say that the energy of the particle is 0, then that means it is not moving at all. So its momentum is 0, and its position is also, because it is not moving, its position is also fixed. So that violates the uncertainty principle. That means you know the position at the momentum and the momentum at the same time. So the energy of a quantum particle cannot be 0. It normally has a 0 point energy. which depends on the physical system in which it is.
It normally has a 0 point energy, which depends on the physical.
Okay, so similar to the uncertainty principle of position and momentum, you also have an uncertainty for the energy and the corresponding time. So here delta T is actually, so suppose you are talking about a two-level system. There is a ground state level and first excited state. So first excited state has certain, what I should say, time period, okay, lifetime of the state. So here delta tau actually represents the lifetime of the state. So there is an uncertainty corresponding in the energy. So if the tau is delta tau, that is the lifetime is very large and the uncertainty in the energy will be less. So normally ground state has infinite lifetime because unless you disturb the particle it stays in that. So there the energy is definitely known. But for any higher excited states you have a finite lifetime. So the energy of the higher excited states is known only to a certain accuracy. It cannot be exactly determined. Okay, so now we come to the operators and observables. So psi we said is a state. It represents or it gives us information about the quantum system. Once you know psi, you can determine other properties for that system. Now how do we find out those properties? So we have to measure. So corresponding, whatever measurement we want to do mathematically, we have a corresponding operator. So suppose Q is some quantity like momentum or energy, we have a corresponding operator which is a Hermitian operator which acts on this wave function psi and gives you Q psi. So this is an eigenvalue equation. So this is a wave operator operating on the wave function giving you Q psi. Q is the eigen energy corresponding to that operator. So if this is an energy operator, this will give you energy value. If this is a momentum operator, this will give you a momentum value. So this Q is an observable, that is any quantity which you try to measure for a quantum system, and corresponding Q is a Hermitian operator. Examples has just, for example, d by dx is an operator. So this operating on this wave function gives you this. So A is the corresponding eigenvalue. Okay. Second derivative you will have. So this will be the eigenvalue. The same wave function again. Second derivative you will have. So this will be the eigenvalue. The same wave function again. So this is the operator and this is the eigenvalue. So this is the real quantity. Measurable quantity.
This is the operator and this is the eigenvalue. So this is the real quantity.
What?
Measurable quantity.
What is represented from the side? What? No, Q is operating on psi. Operating on psi. That brackets have no meaning. It's actually an operator operating on psi and gives you Q into psi. Explicitly that is written.
It's actually an operator operating on psi and gives you Q into psi.
So the two operators that we very normally use in quantum mechanics is the momentum operator, which is given as minus I cross d by dx in 1 dimensions. In 3 dimensions you will have minus I cross del,
which is given as
gradient.
minus I cross d by dx in 1 dimensions.
So this is a linear momentum. Position operator just it multiplies the wave function by just x. So if x is 1 dimensional problem, then it just multiplies psi by x. If it is a 3 dimensional system, it will be multiplying by the magnitude r.
Just multiplies psi by x. If it is a 3 dimensional system, it will be multiplying by the magnitude r.
Other quantities that we come across are the kinetic energy and the potential energy of the particle.
Other quantities that
So correspondingly we have just now seen what is px written as an operator. So correspondingly you have kinetic energy which is written as an operator in this fashion. Potential energy normally is a function of position of the particle. So whatever form, for example, you have say harmonic oscillator, so you will have minus 1/2 kx square, force is minus kx, so potential energy will be 1/2 kx square. So it will be just, so x is an operator, it will just multiplies. So actually kx square will be an operator which just multiplies the function by kx. That's all.
it just multiplies. So actually kx square will be an operator which just multiplies the.
So this is Schrodinger equation. More of it will be discussed by Professor Kandari. So therefore, H is the Hermitian operator, which is called the Hamiltonian. It is the operator corresponding to the total energy, and it will be addition of the kinetic energy operator and the potential
corresponding to the total energy.
And we solve normally this equation, H psi equal to E psi, to get the psi.
We solve normally this equation.
So particle in a box, if you consider, or a free particle, if you consider, the potential energy will be 0. So you just have this, for example, free particle Vx is equal to 0 at all x. You can solve this equation, which is just minus h plus square by 2m d2 psi by dx square. If you have a harmonic oscillator, as I said, Vx will be this. So you have the corresponding equation which is to be solved.
If you have a harmonic oscillator, as I said, Vx will be this.
Okay, I'll just very briefly describe this and then I'll stop. Is normally, if you are talking about a system, say particle in a box, so you get the eigenvalues corresponding to the Hamiltonian of the system. These eigenvalues, so Hermitian operator, the corresponding eigenfunctions, they form a complete set. That means, so they are basis functions basically. So any other function can be written as a linear combination of these basis functions. Okay, and whatever, so when you write it as a linear combination, there will be some corresponding complex numbers multiplying the individual states, and you can write psi.
Corresponding complex number.
Can I have a chalk here?
Individual states and you can write psi.
So suppose I say that you have a system.
So suppose I say that you have a system
Whose wave functions are psi n's, corresponding energies are Ens. Then any function psi of x, I can write a summation of an psi n, n from whatever, how many, whatever, eigenvalues are there. So this is any function. So it represents a particle in that system, but it is not one of the eigenstates. Now if I make a measurement on this system,
in that system, but it is
what
not
will happen?
one of the eigenstates.
I make a measurement of energy, for example.
On this system.
Now all the possible eigenvalues are the energy eigenvalues that I can make. If I make a measurement on that system, I should get one of the eigenvalues. Okay. So what will happen is, when I make a measurement, that means when I operate on this, by this I am going to get an energy eigenvalue, one of the energy eigenvalues. But in general, there is a possibility that any of these eigenfunctions, any eigenvalues can be a result. Okay. So if I make a measurement on this psi x of energy and I get a value En,
So if I get
it actually means that this function, whatever was represented by this function, it has collapsed into psi n. So psi has gone into psi n. The state has gone from psi to psi n.
into psi n.
And what is the probability that I will get a value psi n? Will be proportional to a n square.
And what is the probability that I will get a value psi n? Will be proportional.
And total probability is 1. That means all these a n squares summation, this has to be equal to 1.
That means all these n squares.
So what we say is, when you make a measurement of a particular physical quantity, the system, whatever system it was existing in some state, it collapses into one of the eigenstates of that quantity. So if you are making a measurement of momentum, it will collapse into one of the eigenstates of the momentum, and then it will stay there. Now on that state, if you again make a measurement of momentum, then definitely you are going to get that particular energy. For example, here I have made a measurement of energy and my psi has gone from psi to psi n. Now the system is in the state psi n. Now if I make a measurement of energy, definitely I am going to get the value En, because it is in this state. Okay, and then when you actually talk about expectation values and things like that, later on, yeah, it will remain.
Expectation values and things like that.
So, then maybe after Kandari he is going to discuss one or two problems in quantum mechanics, and next time we will be talking more about eigenvalues, eigenfunctions, expectation values and things like that of operators. So what is the difference between expectation value and the eigenvalue? What are the results that you get when you make a measurement and all these things? We will discuss in next.
expectation value and the eigenvalue, whatever the result that you get in mathematics.
So any questions?
So any questions?
See, normally we use what is David Griffiths, but yeah. So normally we use that, but I can find out. I don't think I. If there are some questions, then I need to talk, but otherwise. Okay.
If there are some questions, then I need to talk, but otherwise.
So books maybe will tell you. One is that we use in MSc.
Books maybe will tell you, but one is that
Gasirovich is also one book which is good. Less mathematics and more of or principles. Gasirovich. हाँ. सिखा दो.
So he's going to use the blackboard. I'll close, so this will shut down, and we will just raise this and you will capture the screen as screen 0 will shut down. Okay. And we will just raise this and you will capture the screen as
I use Blackboard because my handwriting is very bad. That's why I don't use Blackboard. But today I'm not going to use this kind of thing. We have only 40 minutes. But today I'm not going to use. What I will do is I will take words I view of what she said. And then conceptualize what we are going to do rather than introducing few more concepts which already are. Make it light. Make it light. Very good. David Griffiths. Yes. It's a very nice elementary first course book usually used in senior BSc or first year university. First course book. Wherever the mathematics is there, they introduce it. There's a bit of philosophical questions he discussed in the beginning, but then he starts what I call as operational quantum mechanics. By operational quantum mechanics, I mean we try to understand the basic concepts, but I want to compute properties. Finally, what you want to do with quantum mechanics? You want to compute those properties which can be measured. Otherwise, there is no meaning in learning physics. How to do? That's what this does in the best physics. Other questions, how do we take when we advance a bit beyond it? Not other questions. Other questions, how do we take when so we advance a bit beyond? This can go up or no, he has to shut this off. I will place this. Facing this.
Before that happens, I will oh, this has happened. Before that happens, I will oh, this has happened. Motorized. तीन वेळा या बाजूला, तीन वेळा त्या बाजूला, डावी बाजूला. All right, so till that happens, first let us understand that quantum mechanics is non-intuitive. By non-intuitive, I mean classical mechanics as we understand is intuitive. I hit this, I know what happens. I see you, I know what is going to happen if I collide on you. So that will result in scattering. And so if somebody discusses scattering of classical mechanics, Carol to open. So we understand. Classical mechanics by and large is something which we see perceived by our five senses and then formalize. Right equations formalize it. Thermodynamics, I know what heat means. I may not be able to precisely write down what entropy means. That's something different. But basically I intuitively understand. तो ठेवलेले असेल खाली पाठवली माझी एंट्रोपी वाढली घरात मी आपण बघतो सो रोजच so all classical mechanics may be complex may need highly involved mathematics but intuitively that is what we feel. Occasionally there are areas where this may not be true. I do not see an electron by my own eyes, so I cannot perceive how it looks like. Light also we see. We like light. We see light. But actually we don't see light. Just think about it. We actually don't see. We see something else. But still we feel about light. Or electromagnetic waves. Radio waves, that gamma waves. So when I start describing mechanics or behavior of particles which I never see, which behave in a strange way, and as she described, they don't follow the normal laws of motion which we understand as Newton's laws of motion. In some form say the Lagrangian, which is still classical laws of motion, or Hamiltonian, which I can reformulate in Hamiltonian for still it's classical. And Professor Gangal will talk about classical. It's okay with you. It's just that the mathematics slightly involved. Therefore, a time comes when you stop asking question, what is the meaning when I describe it behaves sometimes as a particle and sometimes as a wave? Is very strange way of describing because our language is also limited by what we see, what perceive, what language is developed to describe our experience. So we don't have an exact, precise way of describing. So we say sometimes particles, sometimes that. What is the way out? Try to picturize it as much as possible, but later on raise your hands and start writing a language which is universal, which has unique interpretation. Wave function. Call it psi, whatever. But it's the mathematics which describes Newton's laws are universal. I don't need to. I understand what area is, what P is, and what velocity is. I don't need anything more. I can solve with boundary conditions. When somebody says that I cannot measure where the electron is, at the same time I cannot find where particle momentum. Why is it so important? That's because classical. We have an understanding that and we will take only one particle at a time, nothing more than one particle, one single particle. So quantum mechanics of one single particle. Later on we will see if necessary. Not objects of this kind, which can be easily described by complex mathematics. But then we are not going to describe quantum mechanics of objects of this size with their microscope. They are very complex. They are not going to deal with that. We are going to deal with one particle. So when we say one particle in classical mechanics, it's obvious. And what I am said, as I said, is I am going to just repeat what she has said, essentially in a slightly different language, so that it gets emphasis on that. I am only only less than an hour to do that. So I don't want to anything more than that. So first thing we said is we are going to introduce an entirely different set of concepts which are counterintuitive. Completely. Second thing we said was I need to involve mathematical description. We cannot describe a particle unambiguously unless I introduce some mathematical sense. Third thing that we still want equation of motion. Third thing that we still want equation of motion. That will look very strange. When I write the equation of motion tomorrow, there is an equation of motion because we are used to equation of motion. We are used to time evolution of how our idea is very simple. A particle exists. If the particle exists of mass m, one particle, it has a velocity v or momentum p. I will write vectors whenever required, but they are there. And it evolves in time according to Newton's laws. So there is a time evolution. Now all these concepts get translated into quantum mechanics into a very strange way. That is where the problem comes. But they do get translated. So there are a number of new ideas that will come and I am just going to state them. So the first thing which happens is that how do we describe a state of the particle, one single particle? Now it is obvious in classical mechanics, the state of the particle is described by its position, x, let us take one dimension, does not matter, 3 dimension, x bar, and its velocity or p. Now this is a function of time, this is also a function of time, and that as time evolves, x changes and p changes, and if I know the evolution of x and p over a period of time, you can plot one of them at a time, then I claim that, which is correct, that I have a knowledge of entire system. Suppose I have a very large, take a very large time, and then I look at how x behaves, how p behaves under some force or a potential, and I have that entire knowledge, I have entire knowledge of the system, I do not need anything else to predict what happens. And the prediction of what happens is deterministic. I can predict exactly, is that right? That is what our classical understanding is. If x is here, I am here at this is true, of course, for you and me also, I mean inanimate objects. So you and me are very unpredictable. So inanimate objects, I can predict where it will be after time t, what will be its velocity, provided I know what are the forces acting at and where am I at time t is equal to 0. That is our standard understanding of classical. Is that correct? That everyone understands. This does not work in classic quantum mechanics. That is the first problem, and that is what she said many times, that something collapses and so on and so forth. And that is the question which was asked, can I determine or not? Let us see what happens. So I do not have a picture of particle. Then I introduce, as she said, let us add something else to this. We will come to mathematics part later on. So what was added in the earlier lecture? It turns out that our not only particle ideas, but we are used to electromagnetic waves as waves, leave the electric and magnetic part, but they are waves, complex, moving with a frequency omega or wavelength lambda. We never talked about that as a particle. It is always waves. Waves diffract, waves interfere, that much we know, right? Absolutely no doubt, we never doubted, that is a classical physics again, that all waves interact, interfere, FYBSc, SYBSc, whatever first year college experiment, we can demonstrate that a wave will interfere, it will diffract, because it is a wave it will do it. Particles do not do that, correct? No question about it. But then it turned out, because of the experiments that were mentioned in the morning, that photoelectric effect, that the waves, electromagnetic waves, nobody talked about photon, but they behave, so electromagnetic waves behave like a particle, call it photon. Why we are saying that that is true? Because it carries a unit of energy, quantum, a unit of energy, given omega is the frequency, whatever lambda, then its unit of energy is h cross omega. So, given omega fixed, I have one photon which energy h cross omega, second one 2 h cross omega, twice. You want to increase the energy. So, if I increase the number of photons, my energy is h cross omega. If I increase omega, my energy goes up. So, it is in a quantum of h cross omega. Now, that was introduced to understand photoelectric effect. I can't keep on putting number of photons and say the electron should excite from wherever they are by just increasing. Our intuitive feeling is it's very intense heat. So, intensity is related to us by energy, but that turned out to be counterintuitive in the photoelectric effect. You shoot as many photons as you like, that is, you increase the intensity of the electromagnetic radiation as much as you like. If the energy, single photon energy h cross omega is less than the excitation energy, electron will not come out. For that you must increase omega, right. So, that was the first, that is why Einstein got Nobel Prize. That is a revolutionary idea that the photon behaves like a particle. So, it came from experiments, it was driven by experiment, and there is a lot of that. It is not just overnight it happened, it was driven by this sustained experiment, was much older than that. Having done that, then of course we accepted that the wave, electromagnetic waves behave like a particle. So, this was established that EM wave sometimes, that sometimes business will just leave, but is. So, then it so happened that then mass m electron, that is the revolutionary PhD thesis of the Brouille or the Broglie, as if we pronounce it in a straightforward fashion, the Frenchman. That was a hypothesis, and you can calculate lambda, and as she mentioned, if you calculate lambda, the wavelength associated with the particle moving with the velocity v, you and me, whatever velocity you and me take, the wavelengths would be less than 10 to the power what, minus 30, 40, 50, I do not remember, but it is centimeter. It is so small that it does not matter. So, somebody says if we use quantum mechanics to you and me, it is useless, because it is as good as classical mechanics, that is the wavelength 10 to the power minus 100 centimeters, depending upon the mass, it does not matter. But if you calculate the wavelength of an electron whose mass is much smaller, then the wavelength turns out to be of the order of 10 to the power minus 8, even 9. Now, 10 to the power centimeter, so an angstrom. So, it is so small that when the interatomic distances are of that order, the wave is going to behave as a wave. That means that particle has a wavelength, that wavelength matches with, it is of the order of the interatomic distances. So, when I am describing a microscopic phenomena, so that slit, if it is in few centimeters, it would not matter, you just go through. But if the slit becomes interatomic distance like which is an atomic distance of 10 to the power, again an angstrom is 10 to the power minus 8 centimeters. So, if we are talking about the distances at which the phenomena takes place, at that small distances, and if we are talking about an electron or a proton or a neutron, they all have wavelengths, or an atom like hydrogen sometimes, not always. At that distances, I need to describe it very differently. That is where it behaves very differently, not at level of you and me, microscopic only. Exceptions to this we will discuss if it comes to, not at this stage. So, we are talking about a microscopic phenomena, a behavior of, if you like, of a particle which is an electron having a mass which is much smaller than your and my mass, and what happens if such electrons start interacting with a solid. How do they behave in a solid? They are moving in the potential. So, why solids the way this, why, ask a question, why atom does not break even though the electron rotates, means it accelerates, and as she mentioned it should radiate, it does not radiate. So, we are stable, that is why we are all stable. So, that is a new concept that I have to now deal with the phenomena for where there is a mass m. So, I have a mass m, whatever m is, and then it is associated. How do I understand this? So, do I understand it like a wave associated? Well, that is interesting question. So, there are various ways to imagine or at least graphically see, but the graphical picture should be taken with not with a pinch of salt, but there are specific situations, the ones which he showed towards the end. So, how do I picturize this? All right, let us say I have an electron gun or which is shooting one electron. So, the electron is moving like that, and we said there is a wave associated with it and moving some potential. The best way I can picturize this is I will give you various graphs. These are the graphs of what she wrote as amplitude or wave function. So, I want a function to describe the structure or the behavior, to describe the state of the electron, which I cannot describe by x and t. So, x and t picture at any time technically it is a delta function. It is here that electron, that is our classical picture, right, and it is moving in time this way or that way, has a mass m. But this could be one of the ways in quantum mechanics if you like, but then I will say this is continuous, differentiable, goes to 0, then I will say my electron is somewhere here. Where it is, do not ask that question at this stage. When you ask a question where it is, you are making a measurement, or you are asking a question, if I measure where the electron is, what will I get? We will answer that question. We will have to develop a formalism first to compute what will I observe if I make a measurement to the question where is it, what is the average, and so on and so forth. We will wait for that, it takes time to develop that formalism. But it could be this, it could be a packet of that kind, it could be packet which is very wide of this kind, and it could be packet which is very sharp, another sharper one. I am just drawing some. What is the difference? Well, here the electron is localized in this, here the average, here it is much broader. So, the probability of finding the electron in between this, and I will talk about the interpretation now. Here it is much broader. It is what she said is, now I want to describe the electron, what is the state of the system. So, new concept comes that the state of the system, that is an electron or a particle, is not described by xt, but it is described by an amplitude function which is complex in general, and that amplitude function conventionally 3 dimension 3, I will drop that, x, 3 dimension x, and it has to evolve in time. We still want the equation of motion in time, and now the one which was not there before in space, because this is as a spatial distribution. So, I must find out what is the spatial distribution of my so called state function at any time t. So, I have x and I have t. And that is what I say. Somebody says what is the how do you describe the state of the function? I will say I will describe by a state function xt. It does not tell me anything, it is except to say that now I have a function to describe, and why it